Sorry. All right. Welcome back to class, everyone. Hopefully you had a good week. All right. Today we're going to look at probability. Some of you probably heard of this topic, right? But we're going to go into more detail. I think you also learned it like in grade 7, 8, like it's the last unit or something. But they don't really go very much in depth with it. So today we're going to do that. Okay, here we go. So for those who have never heard of the term probability before, here's the definition. It's just a measure of the likelihood of an outcome. So how likely or unlikely something is going to happen. That's what you can say. And usually probability, like if you were to express it as a number, it ranges from 0 to 1. So 0 as in impossible, so like this outcome will never happen. And 1, it just represents like it's guaranteed that this outcome will happen. So probability will be in between either of those two numbers, or it could be one of them. And here's the term you need to know, independent. So what does independent mean, like in probability terms? So if two outcomes are considered independent, then one outcome does not affect the probability of the other outcome. And here's an example. Say you're flipping two coins. Say I flip one coin first and then the other coin after that. When you flip the second coin, that does not when you flip the first coin, that does not affect the probability of the second coin. Like if it were to land on heads or tails, like the first coin outcome does not affect the second coin's outcome because they're independent. And if you want like an example of like a non-independent outcome, say like you're picking marbles out of a bag. Say they're like two different colors. You had like 5 red marbles and like 5 orange marbles. Say you pick out a red marble first, and then the probability of picking out another red marble or picking out an orange marble would change because of that. Because like the number of marbles inside the bag would change from 10 to 9, and so your probability of picking an orange ball would increase, and the probability for picking up another red marble would change as well. And then for a like general probability, you see this image right here. So the probability of an event happening looks like is usually a fraction. So it's a fraction with in the numerator. You have the number of ways it can happen. So like the number of outcomes that you want that satisfy like the question, and that over the total number of possible outcomes. So that's what probability looks like in general. Are there any questions? Just in general probability, exactly. Yeah. Right. Any other questions? Yeah, Eric, I'm recording this right now, so you'll get the recording after class. All right, let's move on to the next slide. All right, so we're going to look at the rule of product. We actually covered this in our first combinatorics lesson, but we can also use this in probability actually. So in probability, it has a different definition actually. So say the probability that independent outcomes A and B, so they're both independent from each other, the probability that they both happen looks like this formula right here. So we have P. P here stands for probability, and notice that we're using function notation. So we have P at this notation, A intersection B. So this upside down U is called an intersection. This also represents the word, like in English terms, it just represents the word and. So the probability that A and B happen equals the probability that A happens multiplied by the probability that B happens. So here, PA stands for probability that A happens, PB stands for probability that B happens. Any questions about this rule of product? Type it, I think. I know in Google Slides, Google Docs, there's like, if you go to like insert and there's like something called special characters, you can just type in like intersection or something, and then this upside down U should show up. If you're curious. I explained it. It means like and, right? The outcome that A and B both happen. So I guess you could think of like a Venn diagram. I'll put up a whiteboard actually. I'll show you guys. If you guys are not familiar with Venn diagrams, it's basically like you have two circles that like kind of overlap each other, and then in the middle, there's like a section like that represents like A and B. So I'll show you guys. I know some of you are familiar with it already, but for those of you who are not, I'll show you a Venn diagram. So we have two circles, right? And they have a part where they overlap. So right here. So the part where they overlap, so say this was called A. So the stuff in the left circle is A, and stuff in the right circle is B. Right? And stuff in between, so like where they overlap, this is A and B. Or A intersection B for you to use if we were to use mathematical terms. Yes, yeah. So like that. Right? Any other questions? Yeah, we're gonna go over a sample problem that uses this. So here we go. I roll a normal 6-sided die 4 times. What's the probability that I get a 6 for each roll? So it should be fairly straightforward. And if you have an answer, just type in the chat or shout out. Yeah, perfect. I'm not sure what 6 to the power 4 is, but yeah, you can just say your answer is that. Good job, Devin. Let's take it up. Take this up. So clear everything. Let's just undo. All right. So we're looking for the probability that we get 6 for each of the 4 rolls, right? So can someone tell me what the probability is if you roll a 6 on the first roll? So it's the probability of that. Yeah, perfect. Let's see, like probability of one roll. Because on the 6-sided die, you have the numbers 1, 2, 3, 4, 5, 6, right? And trying to get a 6. And so the only way you can get a 6 is just rolling that 6, right? So that's one time. That's one outcome. And then since there are six possible outcomes, right? Those 6 numbers, that's your denominator. So that's 1/6 that you get. That's the probability that you get a 6 on your first try. And for a second try, third try, and fourth try, it's the same number. So then what we do with those probabilities, we just multiply them together. So we have 1/6 times 1/6. Do that 4 times, and you get 1/6 to the exponent 4. Not sure what this exact value is, but that's your answer right here. Any questions? So that's how we use the the rule of product in this question. So say this first roll, second roll, we also have third roll and fourth roll. They're all 1/6. Yeah, there you go. Any questions? Yeah, this is a pretty straightforward question. Let's go into next concept. The rule of sum. We also learned this in our first combinatorics lesson, but it also applies to probability. So here, the probability that independent outcomes, so we're looking at A and B again, but not A and B, but A or B. So the probability that A or B happens is this. So we have probability of A union B. So this U right here stands for union, or in English terms, or. So probability of A or B happens is equal to the probability that A happens plus the probability of B that B happens. But then you also have to subtract the probability that A and B happens. So remember this under this upside down U stands for intersection. So and. So we have to subtract that from this from the sum of A and B. Any questions about this? Yeah, you can also say that way as well. Could put that down right here. Slash. So you could, yeah, as Node 7, right? Who said that? But yeah, you can just express this, so PA and B as PA times PB, like this. Yeah, that would work. Just like that. Any other questions? And if you're wondering why we have to subtract probability of A and B, it's because we actually counted it twice when we found probability A or probability of B. So we could use the Venn diagram to show this as well. So I'm going to draw one right here. Right. Say left circle was A, right circle was B. All right. So if we're looking at probability of A or B, it's just the entire area that they cover. So all of this, we also include like the inside right here. So the entire area that both these circles cover is A or B or A union B. So that's what that's equal to. And when you count probability of A and probability of B, you realize that you count this inner part. So like the part where they overlap, you counted that twice. So that means you have to subtract that area again, just one time. So you have to subtract A and B, just because you counted the overlap part twice when you calculated A or B. All right, is that clear to you guys? Okay, no questions? So I'll move on to the problem. Right here. So I pick a random integer between 1 and 30 inclusive. So it means I can pick 1 and 30 as well. What's the probability that the number is divisible by 3 or 5, or even both? I'll give you guys a minute or so to solve this. Any answers so far? Okay. I'll wait a couple more seconds before taking this out. Okay. Does anyone have an answer right now? Or not quite? I'll take it up with you guys. Okay. Let's do somewhere else. right over here. Okay, so we're looking for a probability that the number I pick is divisible by 3 or 5, or 3 and 5. So one way you could do it is just from look at each of the numbers between 1 and 30 and see if they're divisible by 3 or 5. But that would be pretty tedious. So what we can do is calculate the number of multiples of 3 and also the number of multiples of 5. So that's what we could do. So let's write that down. Number, right, I'll just put m dot as multiples. So multiples of 3 between 1 and 30. And then same thing for 5. All right, can someone tell me how many multiples of 3 are there between 1 and 30? Oh, Bob, that doesn't look like the right answer. So how many multiples are there? How many multiples of 3 are there between 1 and 30? Can someone tell me? Yeah, I think Chengao got the right answer. Includes 30. That would be 10. Yeah, Elaine said 10. So, I mean, you could just count 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. So that's 10. All right. How many multiples of 5 are there? Someone tell me. 6. Yeah. And you can count them as well. 5, 10, 15, 20, 25, 30. 6. Right. So now we could just add these up and get a probability. Right? So we could do 10. Well, actually, yeah. We can express these like as their own probabilities, right? So probability that you pick a multiple 3 would be, so there's 30 numbers between 1 and 30. So that would be your denominator. And then 10 would be your numerator. So we'll keep that as 10 for over 30 for now. Don't have to reduce it. The same for multiples of 5, we could do 6 over 30. And then you could just add those up, right, for multiples of 3 or 5. But you guys probably notice why this isn't like the correct answer. So here we get 16 over 30. Right. But does anyone know why this isn't the correct answer? So this is not the final answer. Anyone know why? It's not 16 over 30. Exactly. Good job, Patrick. Oh, Joy. Oh, it's a principal. 金老师好. Yeah, so as Patrick said, we double counted multiples of 3 and 5, so numbers that divisible by both numbers. And this is just multiples of 15. All right, guys. So we double counted multiples of 15, right? So those are multiples of 3 and 5. And so there are two multiples of 15, right? So 15 and 30. So that means from here, we have to subtract 2 from the 16. And so that'll leave us with 14 over 30 as our final answer. And if you want to reduce that, you get 7 over 15. There you go. That's your final answer. Any questions? No questions? Okay, let's look at something else. So this is called complement probability. So what does complement mean? Complement just represents the probability that the opposite outcome occurs. And usually you can just write a not. So say like I'm flipping one coin, what's the probability that I don't get heads instead of getting heads? The probability that I don't get heads is called the complement probability of the probability where you get heads when you flip a coin. Right? And the way you usually calculate complement probability, so say you're calculating the complement probability of outcome A, this would be equal to the following. So we have probability of, so here we have A superscript C, or like exponent C. Well, I call this a superscript. So AC just represents complement probability. When you see C, that represents complement. That's one way you can think of it. And this is just equal to 1 subtract probability of A, that A happens. And you can rearrange this too. So you get move the probability of A to the left side, and you notice that the probability added to its complement probability is equal to 1. So that's a useful fact to know. Any questions about this? Yeah, Patrick, it'll be 50%. That's nice. No questions? Yes, I'll go up to the problem. Here. They're using Alice, Bob, Carl, David again in the question. So Alice, Bob, Carl, and David, they choose a random different seat in the movie theater and assume they all sit together. What's the probability that Alice and David don't get to sit beside each other? Give you guys a minute or so to figure this out. So we're gonna have to use a bit of combinatorics in here. And you have to use complement probability as well, like just simple, like make the question easier for you to solve. So find how many arrangements there are of Alice and David sitting beside each other. That's the hint. Don't think it's 18. No. Yeah, it is 12. This one, if you get, what's the final answer then? Because it's generic. Why not what? I'll probably use chat. I don't know. Okay, I'll use those next time. Then. I'll use those names next time. I'm not good. Okay, I'm not good at like making up names. I guess, even though I could just search it, but whatever. Too lazy. Okay, let's take this up. Okay, so remember to solve like probability kind of questions. You want to find a number of like satisfied outcomes, right? But in this case, what we could do is find a number of seeing arrangements where Alice and David are sitting beside each other. You could do the opposite as well, like find the number of arrangements where they don't sit beside each other. But I think it might be a bit easier to find the number of arrangements where they do sit beside each other. So we have 4 seats, and we must have Alice and David sitting beside each other. An easy way to solve these kind of problems. So say you have you need two people sitting beside each other. What you can do is merge 2 seats into 1 seat. So instead we have 3 seats now, right here. And say so say Alice. So that means Alice and David could just represent 1 seat, and then we can have Bob and so the others, Bob and Carl. Yeah, and you just have the others put together on the other seats. So just like that. And then if you count the number of seating arrangements with this, you would get 12. The reason why is because you could put this AD, so this Alice and David combination in 3 different spots, right? And for each of those 3 different spots, so say I just chose the middle, you could swap around B and D. B and C, Bob and Carl. You could for each of those 3 spots, you get 2 extra arrangements. So I mean that gives you 3 times 2, or 6 combinations. But then also what you realize is you could also swap around Alice and David as well. So you have David and Alice instead. And so you just multiply this by 2 again. and that will give you 12. So that's 12 arrangements where they do sit beside each other. And for the total number of arrangements, so we're looking for probability, right? We want to look for a denominator, so the total number of possible arrangements is just 4 factorial, right? We're just positioning 4 people in 4 different spots. So that's 4 factorial, or 4 times 3 times 2 times 1. So it gives you 24. And so your probability that they do get to sit beside each other would be 12 over 24. But remember, we're looking at the complement probability, even though you realize it's the same probability, but like the complement probability, you'd have to subtract this from 1. But you get the same answer, 12 over 24, or 1/2. And that's your final answer. Right? Any questions? No questions? All right, let's move on to the final concept. So we have something called conditional probability. Probably never seen this before. But conditional probability is basically this. So we are looking for the probability that outcome A occurs given that outcome B also occurs. And so the way we express this would look like this. Oh, it's side. Sorry. I'm so sorry, guys. Okay, here you go. So conditional probability is just the probability of A given B. So we have A, and so we have a vertical dash. So A dash B just represents A given B. So probability that A happens given that B has to happen. Right. So that's what conditional probability is. And what this is equal to is this fraction. So if you've never seen these dashes before, so the lines that surround an expression, this represents absolute value. And for those of you who've never seen what absolute value means, it just means that the expression inside will always become positive. So say x was 1, so we're looking down here. Say x was 1, absolute value of x would still be 1. But then say x was -1, you'd have to convert that to positive value. So that means the absolute value of -1 would be 1. And if you want like definition of absolute value, it's just numbers that are like countable. So say you're measuring like the length of something like in centimeters. You don't say like -1, right? You still say like -1 centimeters. That doesn't exist. You have to say 1 centimeters. Or say counting the number of, I don't know, anything, counting the number of people. You can't just say you can count -1 people. You have to count at least 0 or 1 people, right? Well, that's what absolute value does. It converts everything to positive. And so when you convert it to positive, that means the probability will be positive as well. Can't be negative otherwise. That wouldn't be probability. And so what the fraction has, in the numerator, we have A intersection B. So remember A and B, or probability of A times the probability of B. And all of that divided by the number of outcomes of B. Right? Any questions about this? I think this might have been a bit confusing to you. Any questions? So in the previous concepts, we were looking at like calculating probabilities with other probabilities. In this case, we're just looking at like outcomes divided by outcomes. So for conditional probability, so you have outcomes of A and B happening, and the number of outcomes of B happening. Right? Any questions? Right? Let's solve a problem with conditional probability then. Over here. A fair 20-sided die is rolled. What is the probability that I get a prime number, given that the number I rolled is odd? Give you guys a minute or so to figure this out. Oh no. Oh yeah, you can say that as well. But it's just from 1 to 20. So each of the sides are numbered from 1 to 20. No, it's not a cheat. Like each side has equal amount to get rolled on. So yeah. No, 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 no. Nope. So just think of a dice from like with numbers from 1 to 20. So 1 to 6. Yeah. Not 9 over 20. No. No, it shouldn't be over 20. So we're given that number I rolled is odd. So in your denominator, you have a number of odd numbers in between 1 and 20. So it's not over 20. It should be over something over 10. Yeah. Something over 10 actually. Let's see. Okay. I'll take this up right now. All right, so we're saying that we're given that the number we rolled is odd. So it means in your denominator, instead of just having like the total number of numbers in between 1 and 20, we're only looking at the number of odd numbers in between 1 and 20. And as someone said, there's just 10 of those numbers. So you count them 1, 3, 5, 7, 9, 11, 13, 15, 17, 19. That's 10 numbers. So our denominator would have to equal to 10. So remember from our definition of conditional probability, oops, in the denominator we have B instead of like total number of outcomes, whereas having number of outcomes that satisfy B, right? So that means usually there would be less. Let's go back to the whiteboard. All right, and so the probability we're calculating is the probability that we get a prime number from those odd numbers. Can someone tell me how many prime numbers are there? Yeah, there's 7, and you can count them as well. Thank you. There's 3, 5, 7, 11, 13, 17, and 19. Yeah, so these are odd. See, these are the prime numbers that are odd and are prime. That are odd and prime. So we didn't count 2. 2 wouldn't be part of it because it has to be odd, right? And this just represents A and B. So you say odd, or like odd and prime, or like prime and odd, in between 1 and 20. Yeah. And so this would be your final answer, 7 over 10. Any questions about this? Ten. It's because so we're not. So question says it's given that the number that's rolled has to be odd. So it can't just be a random number from 1 to 20. So it has to be any odd number. So 1, 3, 5, 7, 9, 11, 13, 15, 17, 19. So those are the only outcomes that we're including in here. Yeah. Is that clear, Bob? Okay, sounds good. Any other questions? Before I move on. Yep, so those are the concepts you need to know. So just conditional probability, we have complement probability, rule of sum, and rule of product. And then just this definition, general definition of probability. Let's move on to some problems. I have 5 black and 4 white marbles in a bag. If I pick out 2 balls one by one, what is the probability that one of them is black and the other is white? So you can first pick out a black marble and then a white marble, or you could just first pick out a white marble and then a black marble. Yeah, looking for those outcomes. I'll take this up. I think this is a pretty difficult problem for us. Being a problem. Let me count. Three more. Hopefully we'll get this by 2:30. If not, that's okay. Let's go back to our whiteboard. So we're looking for probability that we get one black marble and one white marble, and we can switch around the order which we get them, right? So we're looking for that. So we consider our first case where we first get one black marble. So we get our black marble first. So I can't speak, and then we get our white marble. Let's look for that probability first. So let's go over here. Okay, can someone tell me what the probability of getting a black marble is? Like after your first marble. So we have 5 black marbles and then 4 white marbles. What's the probability of picking up a black marble? Assuming that probability of each marble is the same. Yep, Elaine said 5/9. So we have 5 black marbles, and then the total number of marbles in the bag is 5 plus 4, which is 9. Right. And now we want to figure out the probability of picking out a white marble. So now be careful here, because we're picking out the white marble after the black marble. So that means this number has decreased to 4. Let's write down the probability over here. So now what's the probability of picking out a white marble? Can someone tell me? Yeah, Chen Gao's at 4/8. So, or 1/2. So because we picked out that black marble, we have 1 less marble in the bag. So 9 minus 1, that would give you 8 marbles. And then since there are 4 white marbles, we have 4. So that means, I guess we'll rewrite this to 1/2 if you reduce it. And now what we should do with these numbers, we should multiply them. So we're using the rule of product. So basically we're looking at if we pick out a black marble and then a white marble. So because of that and, we have to multiply these two probabilities. And then that would get you 5/18. Okay, now let's look at our second case. Where we pick out a white marble first and then a black marble. Let's look at that. Okay, so someone tell me what the probability is for picking out a white marble first. Yep, Bob and Chengao got it. 4/9. All right. So that's probably picking out a white marble first. And similar, we have to multiply that with the probability that we get a black marble afterwards. So now someone tell me what the probability is of getting out a black marble after that. So here I write down 4, 5. We decrease this number by 1 to get 3. So now what's the probability? Yep, Chen Gao Yi is at 5/8. One less marble, 5 black marbles. There we go. And then we can simplify this, cross these out. That'll become 2. You'll also get 5/18, which is nice. Actually, yeah, these are equal. All right. And so now what we can do with these numbers is we just add them up. So we can have case 1 happen. It's because we can have case 1 to happen, or we can have case 2 to happen. And so because of that, whoops. We have case 1 to happen, or we have case 2 to happen. So it means what we can do is just add these probabilities together. This is a rule of sum. Oops. So this will give you 10/18. And if you reduce that, you would get 5/9 as your answer. All right. Any questions? No questions? Okay, let's look at our next problem. Right here. I have a 50% chance of getting a perfect score on a math test. If I have written 8 tests in grade 10 math, what is the probability as a fraction that I got perfect on at least one of the tests? Give you guys a minute to think about this. And then here's a hint for you guys. Try to find the probability that I don't get perfect on any of the tests. That should be easier to figure out. Oops, did not mean to switch that. If you guys have any answers, just shout out or. Oop, John, sorry, Devin. That's close. Your exponent is incorrect. That's all I can tell you. I will take this up. All right. So probability that I get perfect on a math test is 50%. And if we rewrite that as a fraction, it will give us 1/2. Let me just write right here. I think fractions are easier to work with than percents. Okay. So I gave you guys a hint. So we're looking for the probability that I don't get perfect on any of the tests. All right, so this is the probability that I get perfect on test. So probability of, let's just say A or something. Say A just represents perfect on a test. Oops, my watch. All right. So can someone tell me what the probability is of me not getting perfect on one test? So what is that probability equal to? Yep, Bob got it. Yeah, Patrick, you got the right answer. So it's nice. It's 1/2. Yeah, same thing, right? So probability that I don't get perfect on test. So we call this AC. That's called complement probability. So we subtract. So the way we get this is just we do 1 subtract the normal probability. So 1 subtract 1/2, and it's the same thing. It's just 1/2. Right? Right, now can someone tell me what the probability is of me not getting perfect on all 8 tests? What is that? Yep, Bob got it. It's 1 over 256. So just basically you're multiplying the 1/2 8 times by itself, right? That's the rule of product. Or you could just do, whoops, my handwriting. Or just do 1/2 the exponent 8. And to the 8 will give you 256. So probability that I don't get perfect on any of the tests is 1 over 256. And since the question is asking for like if I get at least one perfect test, that means I can get 1 test, 2 tests, or even all 8 tests perfect. So it means that's the complement probability of not getting perfect on any of them. So now what we can do is just subtract this from 1. And then that would give you 255 over 256. Yeah. So you can also get 2 correct or all 8 correct. Right? That would be the complement probability of not getting any of them correct. Yeah. So that's how we solve that question. Any other questions? All right, let's move on to our next problem. This one we'll use some combinatorics. So I choose 3 cards from a deck of 52 cards. What's the probability that all 3 cards are of the same suit? So if you never heard of suit before, it's just like, are they like all 3 of them are clubs or diamonds or hearts or spades? I'll give you guys a minute or so to figure this out. You're gonna have to use some choose notation here. Yeah, I think it's like the fraction is gonna be like use some really big numbers, so I don't expect you guys to figure out the answer really quickly. So let me just take this up right now. So remember, probability is like number of wanted outcomes over number of total possible outcomes, right? So in the denominator, we should have the number of ways we can choose 3 cards out of 52 cards, and then in our numerator, we would just have number of ways to get 3 cards of the same suit, right? So can someone tell me what's the number of ways to get 3 cards from 52 cards? You just say that's choose notation. You have to figure out what the exact number is. Yeah, check out 52, choose 3. So here we're looking at 52, choose 3 as our denominator. All right, now let's look at the numerator part. So in each suit, so for each clubs, diamonds, hearts, and spades, there are 13 cards. So you just divide 52 by 4 to get 13 cards for each suit. Right. So say I only want 3 clubs. Can someone tell me what's the number of ways to get 3 clubs out of 13 clubs? Yep, Bob got it. 13, choose 3. Right? 13, choose 3. Oh, I wrote it as a fraction. My bad. All right, so there's a number of ways just to get clubs. Now, what if I wanted like also? Well, I have to also count number of ways to get 3 diamonds, 3 hearts, or 3 spades. And so they would actually be the same number of combinations. So what we can do is just multiply this number by 4. We can just add up the number of combinations like that by itself 4 times, or just multiply this number by 4. And then this would be your final answer. I don't think there's enough time to calculate this, but yeah. So this is how you would get your answer. So number of number of ways to get 3 cards out of the entire deck would be 52 choose 3, and that'll be your denominator. And in your numerator, you have the number of ways to get just one suit of cards. That would be 13 choose 3, and then just multiply that by the number of suits, which is 4. So 4 times 13 choose 3 over 52 choose 3 would be your answer. And not going to spend much. I'm not going to spend time calculating that, but you can on your own time if you want to. Any questions? Any questions about this? Mm, no, I don't think you're double counting anything from that. Sometimes with the OR notation, you don't. Sometimes like A and B can just be 0. In this case, it wouldn't really apply. Yeah, yeah. So he probably, I guess an and notation would be like if he got 3 spades and 3 clubs or something like that. But like you can only pick out 3 cards, so that wouldn't apply. Yeah. Any questions? Any other questions? Okay. Let's move on to the final problem. Yep, this is the final one. If I select 3 balls, oh, forgot to share the tab. My bad. Here we go. This is the last problem. If I select 3 balls at random from the diagram below, what's the probability that they will lie in a straight line? And give you guys a minute to think about it. Don't have to come up with the answer right away. Yeah. So anyway. Yeah, I'll give you guys a hint. It was similar to that problem, like I think it was last week. Well, like yeah, I think it was last week, where you had to choose like 3 balls such that they lie in the same row. So it's a similar problem to that. You have to use hockey stick identity. And you know what? I will take this up. I think we could write a solution in this space. So let's think of probability. Right. So we're looking for probability that we can choose 3 balls such that they lie in a straight line. But first, let's figure out our denominator. So the total number of ways we can pick 3 balls from the diagram. And I'll just count them myself. So I believe there are 21 balls from the diagram. So 1 plus 2 plus 3 plus 4 plus 5 plus 6. That should give you 21. Right. So there are 21 balls in the diagram, and we have to choose 3 of them. So can someone tell me the number of ways to choose 3 balls? Just like simply choose 3 balls out of 21 balls. Yeah, Bob got 21. Choose 3. So that would be our denominator. Right. Now our numerator is definitely much more tricky to calculate. And so what we can do is that, so let's go back to our diagram, or let's draw out a diagram. Let's use dots. All right, so 1, 2, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. There we go. Okay. So when you look at this diagram, what we can do is that we can find number of, so we can look at each row first. Each row in the diagram. Those are straight lines, right? Yeah, I'm drawing a diagram on the whiteboard. Yeah, right here. I just use dots instead of balls. It's just easier to, draw. So what we can do is look at each of these rows and find out how many ways are there to choose 3 balls from those rows. We can't do this row or this row at all because we can't choose 3 balls from those rows. Right? We have to start from the third row. And so for each of them, you can express them in choose notation. So say for the first row, you had 3 choose 3. Second row, you had 4 choose 3. And then sorry, I should call it the third row. Third row, 3 choose 3. Fourth row, 4 choose 3. Fifth row, 5 choose 3. And then last one, 6 choose 3. And so you calculate that sum. So plus 4 choose 3 all the way to 6 choose 3. And if you remember your hockey stick identity from last week, this would actually equal 7 choose 4. So that's a way of simplifying this sum right here. Right? Okay. But in this diagram, so we're not looking for like just numbers in a row, like balls in a row. We have to consider balls in a straight line. So this means we have to consider other directions as well. So say I'll choose another example. We consider this. So this right here. Oh my god, my drawings. Sorry. So consider this. We can also consider this, and this. And we could consider the other direction as well. So from here, sorry, it's getting really messy, but hopefully you guys can understand what I'm doing. 5, 6. So if we go for each of those 3 directions, you have the same number of combinations. So you just multiply this by 3. And this will actually be your numerator right here. 7 choose 4 times 3. I keep writing it as a fraction for some reason. Right. So we have 7 choose 4. So 7 choose 4 is like the total number of ways to choose 3 balls from like each row. And then we multiply that by 3 just because we can like do it in different direction. So one way you do it in horizontal rows, the other way we can do it diagonally, and then another way we could just do it with the other diagonal. So that. And then this would be your final answer. Any questions about this? No questions? Not sure if it's 35, Bob. I'm too lazy to calculate right now, so yeah. I think, 7 choose 4. That should be, yeah, 7 choose 4 is 35. I guess, yeah, you can calculate this pretty easily. So 35 times 3, I give you 105 over 21 choose 3. Not too bothered to calculate that right now. Yep, you know what? I'll end the class right now. But actually, looking back at this diagram, I realized that you can also choose this as a straight